Welcome to this paper session on energy communities. We will have two presentations from the AURORAL project and the SINERGY project. First, we'll be hearing from Andrea Cimmino about enabling distributed semantic interoperability, privacy, and discovery for smart communities based on standards. And then we will hear from Miguel on the SINERGY project about 3 living laboratories strengthening research capacity in smart energy management. And then we'll have some time for Q&A, both for people here in person and for people that are in the online audience. So I welcome to the stage to Andrea Cimmino, and you can go ahead with your project presentation. Unfortunately, we don't have an automatic, so I can switch the slides.
Okay. No, there's no problem. Or if you want, you can put here the keyboard and I can roll. Is that reaches? I think it's fine. I can just.
As you prefer. Otherwise, I can.
Yeah, because some slides are a bit quick, so it will be like pass.
Okay.
Okay. Well, thank you for that kind of introduction, and thank you all for attending either in person or virtually. I know Friday, first time, is tough, especially after gala dinner. So I really thank you for being here. So today I will be presenting how to enable different features in distributed ecosystems, such as the semantic interoperability, the discovery, and the privacy, and in particular in smart communities. And I will try to convince you, let's see if I'm able to, that standards are the key enablers for doing this, okay? So before starting to talk about interoperability, privacy, or discovery, let's have a small insight of what these smart communities are, right? So as the smart cities have been growing in the last decade, we have seen that we need to overlap this domain with others that are nearby, such as rural areas, for instance, which is, by the way, the one domain that especially this project focuses on. But there are others, of course. So let's say that smart communities are increased smart cities that also contain overlapping domains, such as I was mentioning, the rural areas. So we will have a huge set of data domains of very wide and spread nature. And a very interesting thing is that in this decentralized environment, we will have data consumers and producers of very different nature. So we will end up, like people, sensor, so we will end up having data being produced or consumed from any of these domains, anywhere, by anyone, at any time. So it's basically a huge mess of people consuming data, requesting data, or publishing data. So in this domain, we will have, as I was mentioning, these different data consumers, and multiple domains. This led us to a very decentralized scenario, distributed one, that is being developed with very heterogeneous technologies. And this is the main problem of the interoperability, right? This heterogeneity can be found in protocols, syntax, models, or even procedures, right? And also the most important part, the understanding of the data. And this is basically what interoperability tries to fill the gap, right? So exchange data and being able to transparently use this data. How we can achieve this? Well, as I was mentioning before, the key enabler for all these things are standards and consensus, both of them. We should always try to consensus on which standards we should use for the different tasks, and try, if there is, use open standards. If there is not, okay, we will need to develop more ad hoc solutions, but always consensus with the rest of the people exchanging data with us, because otherwise we will not be able to interoperate with other systems. If we have a look at the interoperability, we can define these different layers. And for any of them, we should try to find a standard in order to implement it. For instance, for the exchange of data, which is about context and content, or about the understanding, we should try to use the ontologies. The ontologies are the common vocabulary that will allow us to define terms with the same meanings. Okay. About discovery, which is the ability of finding in this distributed ecosystem new peers to start exchanging data with, or with the data normalization. Okay, we will see this layer a bit in detail in a few slides. Also with the validation, it's not enough with exchanging data. We also need to ensure that the data being exchanged follows some restrictions that can go from business restriction to that the data is expressed accordingly to the model we need or we wanted the data to be, right? And finally, we cannot forget the security and the privacy. As you can imagine, this is a hot topic right now, well, I think it doesn't need much more explanation, right? We will see how we have done this. So how we have implemented this in Aurora, in this project. Well, first, Aurora is a project that aims at targeting this kind of nature of distributed ecosystems that have been developed with heterogeneous technology and provide to them a platform that allows them to exchange data transparently and to consume this data transparently. But not only that, also to discover suitable peers to whom exchange data with, and of course, the privacy, okay? We also do validation and more things, but it would take me another talk to present everything. How it looks like? Well, you can see here a bit the architecture. So we have different data prosumers and consumers, and as well here, sorry, I will step in. And then these data prosumers and consumers have their own node, which is local to them, and this will help all the data. So there is no centralized service having data that is not owned by that service, right? And these nodes will exchange data through this middleware that is a peer-to-peer network. And in this way, they can exchange, discover, and perform the different operations. If we have a view, inside this node, these are the components we can see, okay? I don't want to go into too many details here, but basically we'll have a gateway that allows us to exchange this data, a component that is for the discovery. I will talk about this in a few seconds. Another one for the validation, another one for the privacy and the security, okay? And finally, this one that is one of the most important, that is used for the data harmonization that I was mentioning before, okay? And in any one that you see a W3C logo, it has been developed according to a standard. And this is basically the layers this node provides us. As you can see, we have interoperability of data in terms of semantic and syntactic. We have policy interoperability for the privacy. And then vertically, we have the access, the discovery, and the validation. Okay. Let's see how we have implemented all of this. So let's start by the discovery. The problem of discovery is that we cannot start exchanging data if we do not know to whom exchange data with, or maybe we want to know a data producer that is suitable for us because it provides some data we need and we need to discover it, right? So this needs to happen before we exchange the data. How we have implemented this in Aurora? Well, basically using the Web of Things standard that it aims at basically providing descriptions of services, and then it enables several discovery capabilities in distributed environments. And you can see here how we have performed the discovery using the standards. At transport level, we rely on XMPP. On syntactic level, we have the what descriptions, but we can search using JSON path. At semantic level, we can discover using Sparkle, which is another standard from the W3C. How the users of these nodes can make things discoverable? Well, it's really easy, actually. They need to provide to the node, to this component I was showing you before, this document that is basically a document describing the capabilities and the endpoints that this node will provide, the data that will provide to the rest of the network. After doing that, everything that is there can be discoverable by other nodes. How? Well, sending some Sparkle queries. Okay, so if once these nodes have registered the descriptions of their data, then a third node can send distributed queries. In this case, I only put Sparkle to find things. For instance, discover all the things I could access with my node, which is a very simple question, or something more complex like find all the temperature sensors. These are very simple queries in any case, but they can be and get really complex. They could even have temporal restrictions or more type restrictions. Now, once we have done this discovery, we need to start exchanging data. How we can do this? Well, in order to exchange the data, the first thing we need to do is to have a common protocol, okay? And for this, again, we rely on the XMPP network, and then we use or a REST API or a Sparkle endpoint. So we have both. We can consume data with queries or directly accessing the different endpoints. And what about the understanding? And this is the most important part in the exchange. Well, we have implemented ontologies that we have consensus with all the nodes that are in the project. And these ontologies are also built on top of standards. How we have built them? Well, using OWL, and of course, all our data is written in RDF. So everybody participating from this platform will exchange data in this format and using these ontologies. But the problem is that not everybody has data in RDF, right? That's one of the main issues. When I say RDF, usually people think just in triples, but actually we can use very simple formats like JSON LD that looks exactly like a JSON, and that will work as well. So in this case, that we have heterogeneous data sources, we need to perform first an harmonization process of the data. For doing this, we will integrate these sources into the nodes, and in order to translate their data, the users need to provide these files here that are called mappings, that are just translation rules that somehow map how the heterogeneous data is written in an equivalent form in RDF. And in this way, all the nodes can exchange data in RDF, okay? Of course, this process can be bidirectional. So it's not only about publishing data in RDF, but also getting that data and somehow adapting it to your heterogeneous infrastructure. And all this layer of exchange of data now is semantically interoperable. And again, built on standards, built on the standards of RDF and OWL, okay? Instead, or whereas this one is not interoperable. So these different nodes have different protocols. They don't know each other, so they don't even know when to start exchanging data. They can have different protocols, so not even have the possibility of exchange. But even if they do, this, for instance, card has JSON as data model or format, and this one is a CSV. So it's not, they don't fit, right? So here, as you see, it's not only about having the same format, that is this RDF, but also having the same ontology. And this is an overview of the AURORAL ontology. We have followed the LOT methodology that allow us also to extend, if needed, the ontology when new domains come in and we need to add new restrictions. This is a very small overview because it has 12 specific modules for different domains. But just to give you a little glance of what we have there, right? And this ontology, the backbone, is one of the most known standards, which is SAREF, that, well, as you see, it covers different domains. So the good thing is that even if we are based on SAREF, if there is another system that already implements SAREF, they don't need to do anything. They are already interoperable with us. And this is the power of the standards. So now that we have this data harmonization and we can exchange data, we go back to our previous scenario, and this user can directly access through the REST API different values of the sensors. Of course, it can still perform queries for discovery, but now I think this is the most interesting feature. Now we can, with one query, discover, but also access the different data endpoints. And that is really powerful because we can make queries like find all the temperature sensors and get their value, which are located in this building, but in the floor 2, which have a number that is odd, for instance. So the queries here can start becoming really, really complex and really interesting. And finally, a little glance about the privacy. We have implemented it with ODRL, which is also a W3C standard. And also the platform has some access control list policies, which I'm not going to explain, but basically it's whitelist, a whitelist approach. But the ODRL gives us a special flavor for privacy because it allows us in a distributed way, the centralized way, to define policies. When I want to access the data of a node, if the data is protected with a policy, we need to see if the policy actually allows us to access this data. And which policies we can define? Well, first of all, we can define policies with local system data. For instance, you can access my data only during working hours. So if, for instance, we are talking about a university, I cannot see any data of the university outside the working hours. We can define policies with local data, so data that is inside this node. You can access my data if it's working hours. And imagine we have a presence sensor here, and there is someone inside the room, right? But even better, we can define policies to access data that uses local data, but also remote data. So in this case, this node that provides a car can say, you can access the position of my car only if the car is parked inside UPM's premises. But this node doesn't have the UPM premises. It needs to access this other node that has the UPM premises. And this one will only allow to access the data during working hours if there is someone. Okay, so now it starts to get a complex and very interesting area. And the solution, or the way of solving these policies, is totally decentralized. How we set up these nodes with these policies? Well, we have a small component that is the privacy manager, to which we just provide the policies, and that's it. And they are set up. It's not very difficult. And then again, we are back to this scenario, which was our starting scenario. But at this time, as you can see, we can perform all the operations considering the privacy all the time. What about the validation, which is something where I'm not going to give too many details, but just to give you a glance, well, we use Shackle, which is another standard of the W3C that allow us to check if the data is compliant with the model, and also it allows us to perform other restrictions, not only semantic, to check restrictions, sorry, not only semantic, but also syntactic. This is it. I didn't have the clock. I think.
No, it's okay.
Okay. So, in conclusions, the smart community is required to exploit interoperability in order to grow and to actually exploit their maximum value. And the standards and the consensus on the standards, or at the adoption of things that are not standards, are the key enabler for this. Because otherwise, if everybody takes their own decisions, it becomes a mess. It's like a lot of people talking at the same time in a room. And also, it's really important to take into consideration legacy systems when we are taking consensus on the standards. Well, in order to meet all these problems and these requirements, we have presented AURORAL, that, as you saw, basically, I was talking about standards, but mostly are W3C standards. And well, it provides us the features to integrate other systems, and this is really interesting because we can start talking about cross-platform interoperability. And well, it's not only built on the standards, but during the development of AURORAL and still yet, we have used these standards, but also collaborate with them, for instance, with the Web of Things, providing feedback and improving their standards, or providing ideas to improve the standard based on the different use cases and the scenarios we have been living during this project. I think this is it. If you have any questions, I will be more than glad to answer.
Thank you, Andrea. Is there any question here in the room?
Maybe.
Friday morning.
Also, people online, feel free to type any questions in the chat.
If you can go back to just one of the slides with the layers on the schematics, maybe.
I think this one is the most.
Maybe this one. So I'm just wondering. I think I understand more or less regarding semantic, ontologies, etc. And I'm just wondering, what's the from your point of view and thinking on real life applications, and with the mindset of a software developer that works in a software company that does commercial job, okay? So have you seen have you seen any have you seen the developing market of, let's say, for instance, a company that comes to a portfolio manager or a property manager that wants to use IoT technology and has a lot of legacy data, a lot of legacy BMS or sensor, all that he wants to install, and he wants to give an uplifting of maybe a landmark building that he wants to monitor everything technologies because he sees value on that. But then, like the commercial software company can be anyone, says, okay, but we are gonna adopt these standards. We are gonna build data interoperable, and we are gonna use a semantic layer. We can do that, and we will charge you this one. So, is there a market there kind of existing? So, who does this type of? Because what I imagine is that there'll be some, person owns there dedicated to writing code, adapting code, creating services, creating plugins or whatever. And is there somebody that we can, call for quotation to do this type of job?
You
can
call me.
I need to call 3 people. I need to call 3 companies.
Okay, well, so, we can be one.
If I am a property developer, no. I have landmark buildings here in Madrid, prime office is grade A, and super duper connected. And I want to start using IoT sensors in all the rooms, and I want to build my own LoRaWAN network, etc. And I have a technology provider, but I want somebody that builds smart applications and using semantic technologies. I need to pay for that, and I need 3 companies to do that because my procurements.
They ask you 3. I know.
Shop in the market. Is there markets there that you can knock on the door and say?
So to be honest,
provide me with this.
So to be honest, we need to distinguish 2 different scenarios. I will explain both, and I think industry currently is still on the first one. I don't mean they are not already working on the second one, but I think they are more focused on the first one, which is you have a premise like the building and you want to do it smart. That's actually most of the time doesn't need to exchange data between the centralized nodes. When you scale this up and you have a campus full of buildings, then you start needing the exchange of the centralized endpoints because they need to coordinate themselves or maybe check data that is not inside my building, but is inside another node and so on. So I think industry is still adopting the first one, that they are not building decentralized environments like this one I presented. I don't mean this is not being adopted by the industry. For instance, we know some companies that outside that actually they sell this kind of scenario, the second one, right? But I think big companies are still in the first one. And actually you can see a proof of that with the last announcement of Google and Amazon and all these conglomerates of companies that they want to develop Matter. I don't know if you know about this. That is a protocol because they have a lot of devices, and the problem is all devices speak in different ways, and they need to homogenize it. So they have announced they will develop this protocol. There are no details yet, so I cannot tell you if it will use semantics or not. I hope they will. But so this is a problem even big companies acknowledge. So we have very heterogeneous environment, and we need to somehow have a layer that normalizes it. Now, how they will do it, I cannot tell. Are there companies that relies on ontologies and semantic technologies? Yes. And especially Saref is one of the standards most adopted, I think, by the industry. But again, I think most companies still think in the first scenario, in which you connect everything to a hub, and then you perform smart actions on the hub. And the second scenario, which is the one I presented, is one in which you have a lot of hubs, different nodes, and they need to exchange data and perform smart actions, not in one node, but considering all the neighborhood nodes that you have around. And yeah, that's it. So for instance, the car and the premises in the first scenario would be I have a sensor there that sends data to this computer, and then I have here my 2 sensors that sends data to this computer, and everything happens here. Instead, in AURORAL, it's not like that. It's like you have a computer there, I have a computer here, and they need to exchange data in order to perform smart actions. So I think we will move, industry will tend to move to this second scenario, but mostly still in the first one. And in the first one, yes, exactly. And in the first one, it's needed the harmonization of data. But imagine if now it's a problem harmonizing data for one building, imagine if you have 100. Because, for instance, building is actually quite easy to talk, but imagine a rural area in which you have a huge farm and you need to have tons of sensors which are not always the same. So here you have presence, temperature, and humidity, and you are done. But in a farm, you need to have the GPS of the animals, you need to have the temperature sensors, you have to have the weather sensors, if the fence is open or closed. So you have a more wide range of sensors, so heterogeneity increases, and the difficulty, therefore, increases as well.
Okay, thank you.
You're welcome, thank you.
I'm not sure if I completely off. It's only for buildings which are not privately occupied by individuals or so. If I understood this correctly, it's like for universities and industry.
No, that was just an example.
That was just an example.
Yes.
So how do you deal with individuals in the sense of privacy and consent and stuff like that? How does
Well, so when you register, I think this is it. So when you register an endpoint, you want to be public accessible through the network. Okay, you register the discovery slide. You register let's say a document, a descriptor of what you want to offer, but not the value of what you are offering. And then someone, for instance, me, wants to access your data. And this is the whitelist part I didn't explain. So I will request you to access your data. And if you allow me, then I will be able to access your data, white list approach. But then on top of that, you can even define the privacy policies I was explaining. So you can tell me, you can only access my data if you are someone and you provide me the proof that you are that someone. For instance, if you go to a doctor and you want to share some data, you can enable in that moment, I want only to share this data. And then the doctor must prove, and you say to him or to her, this is your proof. So when he requests the data, it will be checked. First, the white access list, and then the proof you gave to that person. I mean, we can make even more complex policies, but just to give you some examples. So it's not something limited to buildings or to universities. Actually, as I was mentioning before, this project aims to focus on rural areas. So we have pilots that are farms. We have pilots that actually are amusement parks, and they somehow study how the crowds are distributed in the amusement park during the different working hours. The opening hours, right? And then they try to see which attractions perform better at which time, if there is a pattern. So what they do on top of that, to me, it's a bit unknown, but that's mostly what they try to do with that. Business intelligence. Yes. I'm just a software developer, so yeah. So any other question that I could answer? Well, in any case, if you want to approach later and ask me anything, I'm available.
Thank you very much, Andrea.
Thank you.
If there's no more questions, maybe later after the other presentations also there's some discussion.
Perfect. Thank you very much.
Thank you. So now we will continue with the presentation. I'm trying to use my keyboard and not the one from you want me to pass the slides or will you do it yourself?
I can do it myself.
Okay.
Here with the
Yes.
courses,
Yes.
no? Okay.
Yes. Okay. So please go ahead, please.
Thank you. Hi, everybody. I'm Luis Blanes. I work for University of Galway. This is formerly called NUIG. We changed our name in the last year. probably due to a semantic strategy on the citations, which influence the decision. So I'm going to talk about a project called SINERGY, which is a very small project and is focused on knowledge exchange between 3 institutions. Okay, it's a bit it's in the topic of smart energy management, but it's a bit different in the way that it's very small, first of all, and it's focused on knowledge exchange and capacity building. So basically the concept is, and it has a particular approach, which is that it has to include a non-EU country, which in this case is Serbia, and the institution is Institute Mihailo Pupin. So the idea is to strengthen the capacity of Institute Mihailo Pupin, which are experts on ICT, and I think probably you know them very well because they are experts on semantic ontology, semantic web, and they are the monitoring and dispatch providers of the Serbian electricity grid. Okay, then there is this kind of knowledge providers, let's call it that way, which are experts on AC/DC grids, which is Austrian Institute of Technology, and us on the part of the building. So and that's that. So the project is finishing this year. There's the 3 partners, and as I said, the main objective is to position the Institute Mihailo Pupin as a leading institution in smart energy management in Southeastern Europe and mostly the West Balkan region. Unlock Mihailo Pupin's research potential in domain of the smart energy management and integrate into the European research area. So there's an emphasis on the project to provide training and opportunities to young researchers. So young researchers normally in Pupin Institute are working on projects, on research projects in the institute, and working for different tasks related to the management of the grid and the power generation in Serbia, and on the side also working on a PhD topic mostly in University of Belgrade. So they work, study, and we also provide some. They have also to provide some inputs to projects. That this is not the only one. They have a number of projects in the portfolio. So motivation and vision is the strategic partnership. So at the end of the three years, this collaboration between the 3 institutions we need to prove that it happened and that we are going forward as a cluster with different projects and further proposals and extending in time the ongoing collaborations. So it involves a lot of human exchange, a lot of lecturings going back and forward, and a lot of exchange of researchers coming to Galway and to Austria, and building the research potential through the collaboration within AIT and NUIG. So as you see here, the domain here is in the demand side and the provision of services, of energy services side, so with AIT, and the building side on University of Galway. So explicitly in this talk, I'm going to talk about one layer of the project, which is the pilot. So we are using 3 pilots in different activities and applying all these ideas of projects and different research activities using the 3 pilots. So there are 3 pilots involved. One is in Vienna, which is the energy-based labs, which is a range of labs in reality. And this is especially this one special building, which is kind of a landmark building for them. Then there is the own campus on Institute Mihailo Pupin, where they basically do semantic technologies. And then there is the campus that I work on, which is the University of Galway campus. This is one of the landmark buildings that we live in. It's the Alistair building, which is dedicated to engineering. And I will extend more, of course, because I'm mostly in charge of that pilot there, and I will briefly explain the other two. So I'm not really an expert on the technologies of the Vienna pilot and on the Mihailo Pipin, but I'm happy to forward any question that you have or any potential collaboration that you have with our partners. Okay. So the first of all, we'll talk about the Mihailo Pipin pilot, which is, as said before, this is an overview of the responsibilities that Mihailo Pipin has to manage and supervise the Serbian electricity grid. They have a number also of patents and proprietary technologies to manage the flexibility of overproduction, mainly hydro, wind, and power, and the management of the grid, dispatching centers in Serbia, the monitoring and the supervision of the distribution network, and the energy balancing as more renewables energy comes into the grid. This is an overview of what the campus look like in a schematic way. It is not really an advanced campus, so it's mostly a traditional cluster of buildings with oil, gas, heating, and with the addition of solar energy, but with a fully operable SCADA system that they manage, and they develop things on top of that. Okay, and here it comes the semantic management on the semantic layer that they build on top of this campus. So key exploitable result. I think this schematic came out of formatting in the conversion, I think, because there was some text there, and this slide just conveys the idea that they have stakeholders in companies in Serbia and in the West Balkan region. So there's a number of countries there, like North Macedonia, Croatia, Kosovo, which is and they usually gather annually, and they tend to provide all the expertise to this West Balkan region. Energy service integration is one of the key areas on Institute Mihailo Pupin, and you will know all of these services that they can perform using semantic technologies, the energy dispatch optimization, and the evaluation and benchmarking, and all on the demand side, so the monitoring of the demand loads. This is what is called. This is a diagram of the energy services integration that they already perform at Institute Mihailo Pupin. So they are experts on ICT supported energy services. Okay, the portfolio of projects that they are involved in. Probably some of you are also involved in some of them. And then we had the AIT pilot. The AIT pilot it's a number of it's maybe three labs, and they are it's a more industry focus, so private manufacturers or of electricity devices or electricity converters, so anything that it's renewable and needs to put power into the grid can be tested there. So circuit breakers and AC/DC converters, and any module that brings electricity back and forward between the AC and DC grids needs to be tested, certified, etc. And they provide this kind of services. There are 3 labs: the high power and high voltage, which is I think is the oldest one, where they test basically the security of the device. So this is a circuit breaker on fire. The Smart S, is for a medium voltage AC and DC devices, mainly focused on PV inverters and also on electric vehicle service stations devices. And then there is the nitty-gritty electronics, which is the low inertia power electronics AC/DC converter. So one of the main focus on AIT is the use. So as you know, the AC is mainly the distribution grid, the alternating current one, and the main so the main project or the main impact of the AIT lab is to test distribution grids using DC networks, so direct current networks. So they are specialized in that, and this is one of the examples of the experiments that they do using simulation and the labs. So this is some sort of load balancing using DC grid, where different front-end providers of energy and then the different type of loads can coordinate using and testing real devices in the lab. One of the approaches is hardware in the loop, which it's tested in this project, this European project called HyperRide. This is another example, which is the medium voltage direct current grid. So this is just testing. This is just the capabilities of the testing, and this is just a huge modelable transformer tester. So any device that provides AC/DC switching gears, it can be tested there and also modeled there. Okay. And lastly, I'm going to talk about the Galway pilot. Of course, this is the pilot I've been involved in during a number of years, maybe more than 10. By the way, this is wrong. And it's located in the west coast of Ireland. The main landmark building is the Alisbury building, and the idea of this building is to use it as a living laboratory for students, teaching and academic purposes. On the right hand side, there is all the range of features and technologies that the building provides, and I will expand more on the latest additions to this. There is a number of renewable energy technologies like PV panels on the roof for Ireland. There are 2 ground source heat pumps. There is a double glazed facade and a number of things like rainwater harvesting. Here there's a huge rainwater harvesting for maybe for domestic hot water and for flushing toilets and so on. And the most important part of the building is that it's highly sensor. So approximately there are more than 1,300, depends on how you split that, to 1,800 endpoints throughout the building. And some of them, typically the relative humidity, CO2, temperature, etc. And for all of the rooms, some very good metering on the labs, and some innovative sensors, which are mainly for instance, the sensors embedded in the concrete slabs, so you can track the thermal inertia of the buildings. This is embedded there in the slabs, and we can track and we can monitor it with the BMS. This is an overview of the things that I have described. This is the sensor of the embedded before construction, before putting the concrete on the one of the concrete slabs. This is from the overview of the building. This is the green area besides the building, and this is double skin facade. And the last edition, which was the geothermal, that I will explain here more in detail, and the PV panel. So all of this is available for data acquisition and further projects, and regularly every year we use that as a living laboratory for master students, postgraduates, etc. Previous project, which is Heat to Gap, what we have used the building for, it's so just to show you the type of research activities we perform using the Alice Perry building as a lab. We want to start from the beginning. So there's a load forecasting using data-driven models done by University of Girona, for detection and diagnosis. So they build a whole app focusing on HVAC systems, on mainly air handling units. Principal components analysis, machine learning by Fraunhofer. So this is a very, very raw approach to finding patterns and clustering of data, which probably zero knowledge of the semantic layer of where the data comes from, or of very basic meaning on the data. So mainly just temperature, but temperature of 500 sensors, and doing some clustering analysis, and which is useful for some purposes, like for instance, finding patterns, trends, outliers, and things that are not conforming to certain rules, which enable us, for instance, to test the temperature sensors of, I think 120 rooms or something like that, and to find out how the disparity of the temperature sensors that are supposed to measure the same temperature, it's a spread, and finding interesting findings for operations and maintenance of the building. ESPR, also there is also the detailed modeling done by the University of Strathclyde of some of the rooms of the building, which involves white box modelings of all the physical features of the building, and using a 3D approach with a 3D visualization that can be exploited further on. We developed our own reduced order model tool, which is called Modsco. It's been used in other projects. And then there was an interesting approach to this, which was done by an Irish company called Sutec, which is basically an IT company that is specialized on asset management, which now is a public company, which is in the stock in the, I think, Nasdaq market, European Nasdaq market in Norway, which focuses on asset management, and they have a very well-developed 3D-based operation tools for property managers. So I think there is also an example of that, which is this one. So what we have there available for research is a legacy database that continuously stores data for historical data. The data is very, so periodicity is 1 minute. So we can track all of this data, and it's open for research purposes. This is the front end of the real-time or nearly real time, because real time is kind of an abstract concept that's probably impossible. But nearly real time visualization of data and surfing in 3D of the different rooms. This is also made by a student, which developed the BIM model, which we continuously improve. Okay, and these are online, nearly real-time data on the room. So on top of that, SUTEC builds some layers of us, according to the property managers or the portfolio managers of the university, that were useful for them to maybe detect occupancy patterns, basically occupancy patterns or anomaly detection on energy consumption, which are very quick and very visual way of surfing the different layers of the building and different floors with color systems that indicates in red that something is wrong, and mostly things that are being sorted all the time, and so on. So the two drone footages, if you want to have a look on the slides, if the slides will be available on YouTube, but you can probably Google Alice Perry engineering building drone footage, and you will end up having this drone footage. The last of the projects, which is finishing now, it's another EU fund project, which is called GeoFit, which is about ground source heat pump system. So this is the project that I was working on from my office, which is this window here. So I had the construction site very handy in that regard, and very time consuming, because obviously you want to see what's going on at every minute. So this is ground source heat pump project. The idea with the ground source heat pump project is to install the ground source heat pump, of course, and to use an existing pipeline, a district pipeline that comes all the way down from this part of the building. Is the time one?
It's the time, it's okay.
Okay, so this pipeline comes to this part of the campus. Then there is a dedicated plant room. It's called the energy center. The energy center, it's big. I mean, in the sense that it can accommodate more energy of heating or cooling production, or we can think about adding more things in that building. So the idea was to use the district pipeline that comes all around this road here and crosses an underpass and provides with hot water to a leisure center that has a swimming pool here. So we ended up using that pipeline to deliver hot water, and using the greenfield, the lawn in the entrance of the building, which is this part here and this part, the lawn, to do the borehole heat exchanger. So at the end, we drilled 18 boreholes plus one core retrieval on to 150 meters depth. This is a closed loop system, and then there all the trenching and pipe work that is needed to feed the heat pumps. We also added a dry cooler on the rooftops so we can explore the switch air to ground, and we can also think about a concept that is not very well explored, which is because this heat pump is not seasonally balanced, so it's a heat extraction only, and needs to be carefully managed, because it is very easy to run out of to shorten the exploitation time, which is normally 20 to 25 years when you calculate ground source heat pump system. So, but if you do not control or properly how you operate and how you extract heat from the ground, it can easily reduce to maybe 5 years or 10 years. So, and this doesn't look good for the exploitation numbers. So we have, and then we can understand better how the regeneration, seasonal regeneration or active regeneration can work using the dry cooler. So just injecting heat into the ground during when it's profitable to do it. So when the air temperature raises above 15 degrees and there is no demand or there is little demand for heat swimming pool. Well, this is one of the pictures of the two drilling rigs at the same time drilling. This is another drill rig that was borrowed with Geological Survey Ireland to retrieve the whole core. So we know what the ground is. This is an overview of the plant room, which is, for research purposes, a bit over-engineered. So we have excess of sensors and energy meters. So we have heat meters in the source side, which is not really something you can find. So we can build and we can construct real COP performances of the heat pumps according to what's the strategy. So we can also split, we have two heat pumps, so we can also split and modulate and stage and cascade them. And this is also part of another application which is developed by one of the partners of the project. Which is actually OG, which is Ileco and Ecoscada products. Another innovation of this is that we wanted to build models, physical models of the thermal behavior of the ground. There are models, simplified models, and we wanted to use some specific data on temperature on the underground to understand what's the load and unload cycle, which is a long inertia and very, very long-term drift in temperatures on the underground, and see if the calculations that are normally done holds true in the long term. So we could see if really the exploration times looks like 20 or maybe more, or maybe less, and build upon and see also how the regeneration, so how the heat injection works, measuring the temperatures in the underground. So in order to do that, what we have installed, and this is a bit of a more extended talk, we have built a sensor equipment using distributed thermal sensor using fiber optic data. So basically, a DTS system is a fiber optic cable. In this case, it's a root cable, it's a reinforced cable that we run across the boreholes, and we dig down the boreholes so we can have a temperature profile every 50 centimeters if we want over time, by sending a laser pulse and reading certain frequencies in the scattered back frequency, like in the light that is reflected in the cable itself. So this is a bit more complex, and it has some photonics theoretical basis there, which is the Raman effect. In order to do that, we had to develop some kind of in-house development of clamps and things to enable the fiber optic not to break and be safely dropped down the hole with the boreholes and with the pipes by non-expert personnel and non-expert operators. And that was a kind of a very good experience for us, and bring the whole fiber optic line here that you can see to the plant room. Finally getting an interrogator is called, and building a database that this is what we are going to start looking at. With that, we have the real temperature profile of the underground, and when we extract it, we will be able to see what's the drift on time of the underground. We have 4 boreholes monitored for that purpose, and of course, this is open for research and as a teaching demonstrator. I mentioned before also that what we will be interested also in this pilot is to introduce some sort of energy storage and or energy storage device, which will be the ideal complement, because we have the heat pump here now. We have a 50 kilowatts PV panel system, which could be also used to feed the heat pump, so we will have 100% renewable heating. Currently is using the current energy mix in Ireland, which is not, of course, 100% renewable. And but as you know, the heat pumps benefit a lot from storage capacity, so that will be a good addition. And also on thinking on the topology of this small district heating network and expanding it. I say that because this small district heating network has 3 or 4 potential consumers, which are 1, 2, and 3 buildings here, and another common building, which is a rowing and river sports centers for kayaking that is coming as a new construction here. So we could potentially think about maybe a low inertia or a low enthalpy network where we can connect this and disassemble or detach this branch as a high temperature, and think different opportunities to expand the network and to really use the network, which was the main purpose when it was built 10 years ago, 10 or 12 years ago by now. As the end of the presentation, I want to invite you to our final Synergy conference, where we are gathering all the research topics during the last 3 years, which it will take place during the 26th to the 28th of September in Belgrade, in Serbia. You can submit a very small paper, extended abstract, the link there, and we will be glad to have more contributions, and we're still open for contributions, probably until the end of August. So feel free to contact me if you want to know what are the topics, or there's a small description, and what are maybe the topics of the conference, and how deep the paper should be, etc. So this is the last slide of the talk for today. Thank you very much.
Thank you, Luis. Are there any questions from the audience?
Yeah.
I'm not sure I understood. Well, why is it if you cut too much energy, I guess, from the your thermal pumps, then you lower the lifetime expectation of the system?
You understood very well. This is
Because
basically
it gets warm, like the ground gets warm.
No, the ground gets cold
It gets cold. Yeah.
because it's a heating-only system. So the lower the temperature, so if you're the lower the temperatures, you're extracting heat from the underground, and the heat flows from the ground to whatever the cold fluid you are pumping, which is the heat exchanger, which is the loop that goes down the hole. So it's a pipe, and it extracts heat from the ground. So if the ground undisturbed ground temperature is, let's say, 10 degrees, and you're pumping at 5 degrees, at the end your delta T will be something like 5, and then coming to the return at 8 degrees. So this delta T is the delta T that the heat pump works on. When you spend 5 years uninterrupted, or 10 years extracting heat, the undisturbed ground temperature will shift low. So the heat pump is a dump system, and it will lower the temperature. So that's inlet temperature that started at 5 degrees. It will lower to 4 degrees, to 3, to 2, to 1, even to sub-zero temperatures, which even in Sweden and the Nordic countries, they're very well used to that, even to the point of freezing the borehole if you have water in the borehole, which is another topic. So another topic because it involves maintenance of the loop. So you have to have a reinforced plastic pipe that is not the standard one, let's say, but you could go sub-zero. But obviously the COP of the whole system and the COP of the temperatures, the longer you widen the gap between the source temperature and the sink temperature, the COP will tend to shrink. So you won't be as efficient as you want. And this kind of glorious COP of 4 or even 5 that you see in the commercial leaflets, it won't happen. So it's 3 or less. So, but this is something somehow that is on paper. It's simulated and it's calculated using specialized software. So and of course, specialized software holds a number of assumptions on heat conductivity of the ground, what happens with the water if there's water flowing through the underground, which is a real big unknown all the time. I can guarantee you civil engineers and geologists won't agree, and you bring another geologist and they won't tell you much until they monitor the data or until they have a core retrieved that they can see what's really the underground, if there are cracks and there are faults. Not to mention if there is an aquifer. If there is an aquifer, this is a really different topic. But with bedrock, there is still a bit of uncertainty, not too much. But what we want to do with this project is to have real numbers on a number of years to see if the assumptions hold. Because normally in ground source heat pumps, especially in residential projects, they are just installed, probably oversized, and left. So nobody cares about what is the shift on temperatures because they are not monitored, and what's the real COP of the system. So thank you. Hopefully I answered the question.
Another question.
I have one question. According to the temperature measurement you mentioned, fiber optics.
Yeah.
How actually, could you tell us more how you place the fiber optics there? Where this fiber optics is placed actually? It's inside the borehole, outside?
Very good question. So, you can do whatever you want, obviously. And in this project, so the setup of the fiber optic has 2 modes mainly. One is a double-ended continuous loop, so a loop that is continuous, so the fiber optic goes from one end to another end in a continuous fashion. So there are no splices, there are no joints in the fiber optic. So you send a pulse in one end and it comes to the other end. In this end is the machine, the interrogator. It's very good because you can do a double-side calibration. So it's quite secure, the calibration. And then there is another, this is the technical setup of the fiber optic wire. So then there is another mode which has one cable, and when you go to the bottom of the borehole, and then the fiber has a splice, so that's a small turn, and they do a splice. So they do a splice with a splicer, with a machine, and there is some disturbance there in the splices all the time. So you can still do double-ended calibration, but it's not as precise as if the fiber is continuous. So having said that, in the first option, when you think about putting the fiber optic down, you are thinking about 2 fibers in reality, because the fiber has to go down the hole and go up again, which
it's a lot of redundancy because in the same part of the borehole you have measurements here and measurements here. So in this sense, it's good. Then in the other side, you have only one fiber, and you just have a termination that it's like a small cylinder with a lot of protections, and that is able to take maybe 100 kilogram load, so it's safe and secure to pull it down the borehole. But then there is less complexity because it's just one fiber. What we have done there is two things. One is to have boreholes that are not active, so there's no pipe in the borehole, and they are passive. So there are two boreholes. Well, there is one borehole 100% passive. So this is a very small borehole that Geological Survey Ireland drilled to extract the core, so it's empty. So we filled it and we put a fiber optic. And this borehole is in the middle of 4 boreholes that are extracting heat. So in this borehole, we will be having the real ground temperature, and we could measure the impact of the surrounding extraction. So the gradient of temperatures will be visible in a very low scale. We are talking about 0.1 degrees over time. So with this, there's no problem where you place the fiber optic. When you place the fiber optic alongside the pipe, alongside a productive borehole that has a loop, there is a problem, of course. First of all, you don't know how the fiber is located when you drop the fiber down. Okay? So you think about, so the fiber, to answer your question, in our case, is in the annulus. So it's in the hole. It's not in the rock, and it's in some place in the hole, in the annulus. So it's the space between the pipes and the hole. So this is grouted, or this is done, filled with water in the case of aquifer thermal energy storage, or the boreholes that they do in Sweden, or filled with gravel or whatever. So of course you never know. If you just drop the cable, you never know where the cable in the end. So like if you have a circle and you have in a cross section and you have the pipes, you never know if the fiber optic is touching the edge of the annulus and touching the bedrock, or if it's twisting or whatever. So it's uncontrolled. With the double-ended continuous loop, what we did was to think about that and to manufacture special clamps. So we have CNC machines, and we order also some of them, and we have done a special clamp that holds the fiber optic every certain 10 meters or something like that. I have a lot of slides to just show you in the picture that was not in this presentation. So we can have certainty, at least we can have certainty that the fiber optic is located at a certain distance, that we can build a model on that. So it's not at the edge and it's not touching the loop. It is quite difficult because the most thing that you put in the borehole, the most difficult and the most dangerous become. So the downbore borehole equipment, it has to be very specifically done that it can drop down and not present any problems for the drillers or any claims, and that also the fibers can be dropped down safely. People in the oil and petrol industry have a lot of experience on this equipment, not us. So what we did was to produce what we thought it was good for the purpose of what you are asking for, which is having some certain control of where the fiber optic is in the annulus.
Thank
I
you.
hope I answered.
Yeah.
Are there any more questions? Not online. Here in the room? No? Okay, so thank you very much, Luis.
Thank you.
And we can close the session here. You can, of course, keep discussing during the coffee break, which will start in 5 to 10 minutes. So